Bismillah ar-Rahman ar-Rahim. Welcome to Tahar Scholar. We are ثلاثاء 26 سبتمبر 23 بماليزيا. Tuesday 26th September 23. So we are in the series number 1 of chapter 1, the root of an equation, and we will solve exercise number 3, the mass of a parachutist. Let us first make a pause. We go to the screen, read the exercise, and then come back. So let's recall exercise. Let's read our exercise for this tutorial, exercise number 3, and then we come back to our setting, our regular setting. A parachutist falls vertically with a velocity defined by the following expression. So we give the expression of the velocity, Vt, equal gm over c times 1 minus the exponential of minus c over mt. So the velocity is a function of t, and g and c are constant. M is the mass of the parachutist, g the gravity acceleration, and c a coefficient characterizing the air resistance. It's an empirical coefficient obtained by experiments. As numerical values, we'll choose g equal 9.81 meter per second squared, and c equals 15 kilogram per second. What is the question? Determine the mass m of the parachutist such that his velocity becomes 39 meter per second after 7 seconds of falling. And I give you a hint. Formulate the problem in an equation where the mass is the unknown. So now let's come back. You can make a pause, read it carefully, and then follow me. So let's come back. Okay. Okay. So we are given the exercise. We are given the velocity of the parachutist. We have a parachutist falling, and its velocity of the parachutist is given by the following expression. V, function of t, equal gm over c times 1 minus the exponential of minus c over m times t. And g is the acceleration, gravity acceleration, which is a constant, e acceleration to 981 meter per second square, and c is an empirical coefficient, empirical coefficient representing the resistance of air, or characterizing the resistance of air. Empirical coefficient characterizing the resistance of air, and its value is 15 kilogram. So C depends of the shape of the parachutist and the atmospheric conditions like wind and temperature. So it's obtained by experiments, empirical. Okay. And what is our goal? Our goal is to find the mass of that parachutist such that the velocity at t equal 7 seconds must be equal 39 meter per second. There is someone observing the parachutist falling, and he noticed with an apparatus that its velocity after 7 seconds of fall, that his velocity is 39 meter per second. And our task is to find the mass. Now this is the exercise. But first of all, we will not solve it directly. We first explain. It's not the task of the exercise, but for pedagogical reason, when you have a model, try to understand where it comes from, how we get this velocity. So that would be the first part of the exercise. And then we find the equation for the mass. And then the third part, we solve it using Abou-Kamel's method. So we need first to understand the physics of the parachutist. So first of all, albeit it's not the task of this exercise, of this series, to delve in the realm of physics and calculus. But in the real world, you need these skills, not only numerical analysis. So it's a good occasion to practice your knowledge, this basic knowledge in physics and calculus. So let's do the model, physical model. So normally we have a parachutist falling in the air. This is its parachute, and this is its parachute, and this is the axis Z of the altitude, and let's note it Z. We have here at t equals 0, the velocity equals 0, and at t equal 7 seconds, the velocity is 39 meter per second. With the velocity, by definition, is the variation of Z, of the altitude of the parachutist. So Z point, by definition of the velocity. So instead of studying the parachute and the parachutist, which is very complex, of course, we simplify it to a single mass M. And what kind of force is applied to this mass? Its weight, let's call it Fw. Fw is mg, it's the weight. And the force that opposes the movement of this mass due to the parachute. Let's call it Fr, resisting force, Fr. Here we have to make a hypothesis that this force is proportional to the velocity. So this is the first model. We can also, in a second model, when the velocity is large, we can say that it's proportional to the velocity squared, to the square of the velocity. But in this simple model, we just write minus c v. Minus because it is opposite to the movement, and c is a constant, an empirical constant. So a constant. And let us also observe that the force Fr due to the resistance of the air is variable. It starts with 0 and it increases until it is equal to the weight. The weight is constant. When Fr and Fw are equals, we reach a velocity called the terminal velocity. So, albeit I draw it like a narrow constant, but actually it varies with time, increases. We'll come back to the terminal velocity later. But for the moment, let's see the forces acting on the mass, Fr and Fw. Okay. And then what we will do, we apply the law of motion, the second law of Newton, the law of motion. So we apply the law of motion, which tells us that the sum of all forces applied to M, the resultant force, must be equal to the mass by times the variation, the derivative of the velocity, the variation of the velocity with respect to time. This is the law of motion. The sum of the forces, the resultant force, is Fr, the resistance due to the air, and Fw, the weight. Let's write here the resistance of air. And this is equal to minus Cv plus mg. And these two equations will give us the following: minus Cv plus mg equal mv dot. Or, let's continue here. We have minus Cm. The law of motion gives us the following equation: Vt plus g equal the velocity dot, the derivative of the velocity. And what is that? This is an ODE, an ordinary differential or ordinary differential equation, where the unknown is Vt. T is the independent variable. There is one single independent variable. That's why it is called ordinary differential equation. The independent variable, and V is the dependent variable. It's the unknown. So we have our equation, our ODE. Let us solve it to find the expression of the velocity. We solve it analytically. This part we are using calculus. So solving analytically our ODE. This is a first order, because there is only the velocity, the derivative of the velocity, no second derivative, third derivative. First order ODE is a first order ODE, and it is linear. There is no v square or sine, and is linear. So in this case, first order and linear, we can use an analytical method, very simple to solve analytically. But in general, an ODE, it's very difficult when it is nonlinear or second, third order to solve analytically. We use numerical methods. But in this case, in this particular case, it's very easy to use calculus to solve it. First order ODE and is linear, so it is easy to solve analytically. It is easy to solve it. How we do that? So first of all, we separate the variables. We have V and T. V the dependent and T the independent. So I write this in this way. Minus Cm V plus G equal dV dt, which implies that dt equals 1 over minus Cm V plus G dV. So we have here only V, and here we have only T. We have separated the variables. So for that, variables separation. This is the first step. There is 4 steps. Variable separation. And then we need to integrate. If you had only V in the denominator, we can integrate easily. It's the natural logarithm of V, or the absolute value of V. But we have this constant. So what we do, we change the variables. We make a change of variables. So we introduce a new variable, W, by definition, is equal to this quantity in the denominator, minus Cm V plus G. So we introduce a new variable, intermediate variable. Later we will come back to V. Introduce a new variable to make the integration easier. Introduce a new variable. And then, okay, we have that equal W, but dV. We need also to eliminate dV. So we calculate dW, the differential of W, equal the derivative of this with respect to V. That's minus Cm times dV. This is the definition of differential. The differential of any function of one variable, it's the derivative times the differential of the independent variable. Here the independent variable is VW, is a function of V. So this implies that dV equal minus M over C dW. And now we have dV and this quantity, we replace them with W. And we get, and hence, our equation becomes dt equal 1 over W, and we replace dV by this quantity, minus MC dW. We can take this coefficient to the other side, and it becomes minus C over M dt equals dW over W. Now we can easily integrate. So third step, we integrate both sides. We use the indefinite integral. So the indefinite integral of minus Cm dt equal the indefinite integral of dW over W. So here is the indefinite integral. And here is very easy. It is the logarithm, natural logarithm of or ln of the absolute value of W, because the quantity here must be positive. strictly positive. Otherwise, the logarithm will not be defined. W here can be positive or negative. We don't know. In general, it can be positive or negative. So we take the absolute value. It cannot be equal 0. Otherwise, the integral is not defined. So log ln absolute value W plus a constant, C1. Always the integral is known with an additive constant. If we differentiate this quantity, we get this one. We get the 1 over W, the integrand, or integrand, the integrand. And here it's very easy, minus Cm times T. Okay, but we need a relationship of W function of T, not T function of W. So what we do, we introduce another constant. And we write minus C over M times T equal logarithm, ln, logarithm, natural logarithm of W. But here we write ln of C2. What is C2? C2 by definition is the exponential of C1. It is always positive because exponential of a number is always positive. When we calculate its natural logarithm, we find C1. So logarithm of C2 is C1. So we replaced C1 by natural logarithm of C2. This is what we have done. We introduced a new constant. But why? Because this is to help us remember what we are doing here. So logarithm ln of A plus ln of B, two constant, two positive numbers, ln of A plus ln of B equals ln of AB. So we can introduce them both and we get C2 absolute value of W equal minus CMT. And we know also that the opposite, because we want W function of T. We know the opposite of ln. The opposite, not the opposite, I mean the inverse. The inverse of ln, function ln, is exponential. That's what we have done here. Is exponential. Means that if we have x equal ln of absolute value of W, this is equivalent to say that the absolute value of y equal exponential of x. This term is always positive. So that's why we use absolute value. We apply that here. This is y, and this is x. So we have C2 absolute value of W equal the exponential of minus Cm over T. Now this is x, and this is y. We have applied the inverse of ln, and the vice versa, the inverse of xp is ln. So these two quantities, two equations are equivalent. And we get W. We eliminate the absolute value by writing plus minus 1 over C2. can be positive or negative, and this quantity E minus C and T. E to the minus C over M times T. And this is another constant. Let's call it K. It's another constant. It can be positive or negative. So we can write here K exponential minus C and T, W. And the solution of an ODE first order is always contains always a constant. Is known always with a constant. And we eliminate this constant using the initial condition. So let's suggest here another notation in mathematics, in calculus. So we have used C1 in the integration. Then we have used C2 by definition is exponential, the exponential of C1. And then K by definition is plus minus 1 over C2. So the constants are equivalent. If you find C1, we can calculate C2 and find K, and vice versa. If you know K, we can deduce C2 and then C1. So we have one single constant, but in different form. And our result at this step, at this part of reasoning is that. But we need not W, we need V. So our original variable, the velocity. So 1, 2, 3, 4. We come back to our variable, the velocity. And we write it, it's here, W, replace it. So we have minus Cm, velocity, plus G equal K, the exponential minus Cm, and this is W. We need to eliminate K using the initial condition. The initial condition, in our case, on the parachutist, when he start his fall, its velocity equals 0. So velocity at t equals 0 at the start of the movement is 0. So we have minus Cm 0. We replace V by 0 plus G K E minus C over M, and we replace T by 0. And we get this becomes 0 and this becomes 1. So we get K equal G. So our constant is equal G. We didn't know before, it can be plus or minus a constant, positive constant, but in our case, because of the initial condition, it is positive and it is equal to G. So we replace it again. We have then minus Cm V plus G equal G, no K anymore, minus Cm, and we solve for V. It's very simple. We get minus Cm V equal G times E minus Cm e to the minus C over M times T. This is T minus 1. Because G1 comes here, it becomes minus G. So, and then V equal Gm C. This becomes M over C. And because of minus, we write 1 E minus C over M and T. And this is the velocity we have given in the exercise. It comes with a simple hypothesis that the parachutist can be modelized with a single mass, and the only forces applied to that mass is its weight and the resistance of air. And the second hypothesis is that this resistance of air is proportional to the velocity, not to the square of the velocity. So, because some models, when the velocity is large in aerodynamic, call that the aerodynamic drag. When the velocity is large, the resistant force becomes proportional to the square of it changes parabolically, not linearly with the velocity. It becomes proportional to the square of the velocity. So here it's very simple model, and that's the result. Okay. I've done some calculus, but not a big deal. So, but let's, it's not also requested, but let's draw the velocity with respect to t to see what is the terminal velocity. So this is the curve of the velocity, with respect of time. And we can observe that it has an asymptote where the velocity becomes a constant. We note it change very slightly, tends to constant. It increases rapidly, exponentially, between 0 and 20 seconds. And this velocity is called the terminal velocity. And if you recall, the equation of the velocity is gm over c 1 e minus cm t. So when t tends to infinity, this term, the factor, tends to 1 when t tends to infinity, when t increases. And the velocity tends to this term. This is the terminal velocity. And I draw this curve for the case where m equal about 83 kilogram. And we need to know all the constant, not only g and c. We need also to know m in order to draw. If we change m, the curve also will change, but still we have an asymptote here that tends to this term gmc. This is the terminal velocity gmc. So it's not requested, but it's good to understand the physical model. And then the second part, let's find the equation of the mass. The equation of the mass. To find the mass, we need first to find its equation. Okay, let's see my notes. How we find the equation of the mass? We have observed that the exercise tells us that the velocity at t equals 7 seconds becomes 39 meters per second. That is somewhere here. And the velocity is increasing. At 7 seconds, its exact value, is 39 meters per second. So what we do, we replace these values in the expression of the velocity. So we get 39, so this will lead to 39 equal mg over c times 1 minus e to the minus 7c over m. 7 is the time, and 39 is the velocity. And we know g and c, so we have here 39 m 981 over 15 times 1 minus e to the minus 7 times 15 over m. And this gives us 39 minus, not minus, 0, the ratio here, 0, 654 m times 1 minus e to the minus 105, multiply 7 by 15, over m. So the only unknown here is m. So we write it in equation. It becomes, so our equation reads the following: 0, 654 m times 1 minus e to the ratio 1 minus 105 over m minus 39 equals 0. Find m. So here we have x is m. This is the unknown, and this is the function of m. It is a complex equation. We can't solve it analytically. It's impossible. We need an analytical method. We have learned Abou-Kamel's method. Use it. So here comes the numerical method. So once we have the equation, we have understood the physical model, we have our equation. Now we do what we have learned, very simple, basic method. We draw the table. Let's draw it quickly here. So, okay, we have our equation and we have our table, Abou-Kamel's table. But we need an interval here. So we can reason in the following way. Now this is a parachute, so the mass it should be more than 50 kilogram. Not a teenager, of course. You cannot have a teenager as a parachutist, and not exceeding 100 kilogram because we will not support, will not bear the forces acting on him. Or we can simply draw the function, draw this function. M here is x. M is x. And draw this function with respect of m with MATLAB, and we can see that that our mass is between 50 and it cuts the x-axis, the m-axis, between 50 and 100 kilogram. So this is our interval because we need both equation. I have showed how we obtain the equation, and also it's very easy here to find the interval. You just draw it or reason physically that this must be a strong man or strong woman between 50 and 100 kilogram. So this is the input: 50 kilogram, 100 kilogram, and 100%. And when we replace here the values, they must be of different signs. Otherwise, this is wrong. But it is true, of course. I have already drawn the curve. So let's replace here 50 here and here. We get the value minus 10. So we are applying the method. I have applied it in the exercise 1, in exercise 2, in the example, I think lecture number 2, section 1.3. So we have a good knowledge of the method now. So minus 10, 3, 4, and same for xu. Replace it in f. We get 3.514. 3.514. And then we calculate the root. X here means m. The first root. Fu fl 514 minus 10 304 in the numerator and denominator. And for the x's, 50 and 100. And we get the value 87,285. You can practice with me with the calculator if you want. I take this value here, I report it here, 87,285. And then I replace it in the function to get the image 0,942. I check it's bracketed between 50 and 100, and the sign here it was negative, and here it becomes positive. Then the rule of the signs for the next interval, it's positive, and it's positive, FL and FR. Negative, and here is positive. So FL and FR, they have opposite signs. So we are at the left. The curve had crossed the x-axis between FL and FR. So the lower bound not change, and the upper bound we take XL and FR and we put them here, the new upper bound. So the new upper bound is 87,285, and its image is 0,942. XR2 again, FUFL 0,942 minus 10, the 3. Be careful here, minus. And in the denominator, same. 0 minus 10, 304. And XLXU 50 and 87, the new upper bound, 285. And I found 84, and my notes in front of me, 84.162. 84.162. Replace it in the function to get the image, and I get 0,234. FR is decreasing, and XR is always bracketed between 50 and 100. Now let's calculate the error. It's the current minus the previous over the current by 100%. And I find minus 3.7%. The current value of XR minus the previous over the current. It's relative to the current. And then you multiply by 100%. At the right or at the left, positive and still negative, so at the left. And we said that the method generally will not oscillate. And we take XR and its image, 84.162.162 and 0.234. And I apply again XR3, 0.234 is our new FU, and FL still minus 10, 304 in the numerator and denominator. And XL 50, and XU, the new XU, 84.162. And we obtain the value 83.403. We report it in the table, 83.403. We take it again in the image, in the function to get the image, and I found 0.057. Assess the error, calculate the error, assess the progress, where we are, 83. For the current, 83.403 minus 84.162, the previous, over the current, multiplied or times 100%. And I found minus 0.09%. So we are here less than 1%. We stop our calculation, we stop the iteration. We don't need to continue. So in 3 iterations, we get a solution with an error less than 1% in its absolute value, less than. So it's really powerful, and it is a rather complicated equation, but we got the solution in 3 iterations, an approximative solution. So let's write it here. Our mass, this is our main task, our mass, or the mass of the parachutist. Our mass M is 83.403 kilogram. So it's about 83 kilogram with an error, approximative error at the 4th iteration equal to 0.9%. And that's it for the series. I finished series of exercises dedicated to chapter 1. Next week, inshallah, I will start by an introduction to MATLAB in 2-3 practicals. I have not yet filmed the practicals, but I guess 2-3 practicals, and then we come back to our chapter and we do the practicals dedicated to this chapter. In order to grasp the method, you need also to know how to implement it and how to use it in a program, in an environment like MATLAB or Octave. See you inshallah next week. Peace.